our new unit that we're getting into is going to be transformations, okay? And before we get into transformations, we're going to talk about symmetry because it's kind of related to transformations, right? It has to kind of do with like rotations and reflections and stuff like that. And so it's kind of neat because there's lots of fun symmetric things in the real world, okay? So, for symmetry then, we're going to talk about different kinds of symmetry. So, a figure that can be folded so that it has two parts that match exactly, okay, has what we call line symmetry, right? Or also known as sometimes reflection symmetry. Reflection symmetry. Okay. The idea being that when you can fold something like that, okay, you're kind of reflecting the object onto itself, okay? So looking at the Batman symbol right here, right? Okay, we have some line symmetry, right? And where would the fold have to be for this Batman symbol right here in order to kind of like reflect it onto itself? So yeah, Maria? Yep, right down the middle, like so. And we can draw in that line symmetry, right? Right down the middle. Are there any other line symmetries for this, though, Maria? Is that the only one for this? Don't know? What do we say? Is there any other line symmetry for this one? No. Yeah, no, not really, no. Nope. Okay. What about this butterfly right here? This moth, I think, is actually what it was when I pulled it off the internet. Okay. Same kind of thing, right? We have some line symmetry, like right through here. It looks pretty symmetric there. Of course, we know it's nature, so it's not going to be exactly the same, but it's pretty darn close, right? I really can't see much of a difference there between the two things. Okay, and then we have this right here. So where's our line symmetry for this one? So yeah, Michael.
Aren't there two? One right down the middle and one going horizontally?
So yeah, sure enough, it looks like, right, we got a vertical one there. And then because of the reflection in the pool, we really have like a line symmetry through the middle for the most part. Now, obviously, you know, someone would be like, "But Mr. Widmeyer, there's a wavy part there." No, I understand, but you know. But yeah, there it is, the Taj Mahal, right? It's got symmetry. Yes, Patrick.
If you look at the background, though, it's not the same on either side. Of the,
I see what you're saying, like the trees here, maybe, and like the trees here. That's true. Very true. Yep. The palace itself, strikingly symmetric, though. Strikingly symmetric. Okay? So, moving on down here a little bit. So, figures can have no line of symmetry, right? Only one line of symmetry, and some have two or more lines of symmetry. So, for example, if you look at this like kind of cartoon cutout of maybe like an orange or, I don't know, a grapefruit or who knows what that is necessarily there. Okay? So how many lines of symmetry do we have in this thing? Well, let's see. I can see like one through the middle, like one vertically, right? And we have like a horizontal one, right? So that's pretty easy to see, okay? And maybe like a diagonal one this way? And like a diagonal one this way? So let's see, I'll start counting. So 1, 2, 3, 4. So I see 4 lines of symmetry there. Yeah.
So you can do it in between like the food?
Yeah, in between the little pieces there, exactly right. We can actually go more, right? So we can say like, okay, well there's one right there. So we'll call that like 5. And another one right here. So that's 6, and then, oh my goodness, 7, 8. So there's really 8 lines of symmetry to that bad boy. That's pretty impressive. All right. So how about you guys go ahead and do the little snowflake there that I got for you? How many lines of symmetry? And again, you know, obviously it's not perfect, okay, but you can, you know, judge it for how you want to judge it there. All right. It's not perfect, though. Yeah. There you go. See how many lines of symmetry you can draw in there. Okay. So Drew, how many did you get?
I got 6.
6? Yeah, me too. That's what I got. Okay, 6. And again, it's not perfect for sure, because we can see, like for example, here on this arm of the snowflake, it's got like 2 little bumps right there, but only 1 bump there. But you know, again, for the most part, it does have 6 lines of symmetry there, right? I think that's an actual snowflake too, an actual like, you know, bless you, snowflake under a microscope and stuff like that. So, what about people? How symmetric are humans? So it turns out, if you flip the paper over there, right, bless you, people have actually like used computer programs like Photoshop and stuff like that to look at the symmetry of people's faces, specifically celebrities, I guess. Okay, so you can see up here, this is Ronald Reagan, right? So the original photo is here on the left. Okay, and then this middle photo, that's his left side of his face, like, reflected. And then the right side of his face is also reflected. And it's amazing the difference there, right? Now, granted, his smile is not the most symmetric smile there, okay, but it's kind of interesting how much of a different face that they make. Let's see, here we have Anne Hathaway. Okay, I think the top picture is the original, and then this is like the right side reflected, I think, and this is like the left side reflected. And again, very interesting there. And then here's obviously labeled for Salma Hayek. Okay, so the original left symmetry, right symmetry. Again, it's very interesting the difference, the subtle differences. And you got Denzel Washington down here, who looks almost identical in his normal to his right face there. I don't know, it looks almost the same. And then just his left face is just a little more narrow. But his face, interestingly enough, Denzel Washington's face is one of the most symmetric famous person's faces, at least. So his face is one of the most symmetric among all celebrities and stuff. So it's kind of interesting. There's like all this, like I was reading some, like there's all these articles about like, you know, beauty and stuff like that, and how we, you know, determine it and stuff. And they were saying like, oh, well, maybe symmetry is a major factor in beauty. But then you can look at some people that are considered beautiful, and their faces aren't that symmetric. So, you know, there's, I guess, also we can consider flaws to be, you know, sometimes important too in considering beauty. It's interesting. But anyway, Denzel Washington, one of the most symmetric faces. Okay? And you can look up many celebrity faces. So tonight, if you're bored, or if you are really intrigued, you can like look up, I just, you know, typed in like celebrity names and then symmetric face or something like that, and then they had all these to look up. So yeah, anyway, there you go. There's probably apps and stuff like that you can probably do for yourself too to make your own symmetric face. So moving on though, a figure that rotates onto itself before turning a full 360 degrees has what we call rotational symmetry. Okay, or also point symmetry is another word. Okay, rotational symmetry or point symmetry is what we're going to fill in there. Okay. So now, why do you think we don't consider 360 degrees to be rotational symmetry? Why don't you think we consider 360 degrees to count for rotational symmetry? Patrick, what do you say?
Because once it's been rotated 360 degrees, it's in the same position it started.
Right, and like everything would then have rotational symmetry if we considered 360 degrees as, you know, as a possibility. Right, so it's got to be less than 360 degrees in order for it to have rotational symmetry. So you can look at some examples here. For example, this. Okay, can you guys read what that says? Yeah, it says mathematics, right? Well, if you rotate your paper 180 degrees, it still says mathematics. That's pretty cool, isn't it? Okay, I think that's called an ambigram. if you guys have ever read the Da Vinci Code, I think there's a Illuminati ambigram in that one. So, okay, too spooky for me, but there you go. Okay, so yeah, exactly. So mathematics though is one. So the point of like symmetry, the rotational point, will be like right there in the middle, right about that E that kind of rotates there. There's actually a whole like I guess there's like an art to writing these words in such a way that they do what they do, that you can read them one way and read them again another way. Okay, and so yeah, so of course we have it this way once, and then this way. So there's two different ways to kind of see it, and so the 360 degrees divided by 2, that gives us then 180 degree rotational symmetry. Okay, it kind of takes us 2 turns. We see it twice before it goes all the way around. We see it in 2 different ways, I guess. The original and then the turn. Okay. This symbol, right? We're familiar with this one, hopefully. That's the recycling symbol. Okay. So the point of rotation for this one would be right in the center, right? Right there. And how many times can we turn this before we get back to the original? So let's see here. So we can do it 1, 2, and then 3 turns to get back to the original. So how can we figure out what the actual degree of rotational symmetry would be here? What can we do? If it takes 3 turns, yeah. Exactly. So if it takes 3 turns to go a complete 360 degrees, then we'll just do 360 divided by 3. You got it. Good job. Which is 120. Okay, so 120 degree rotational symmetry. Okay. How about this hubcap down here? How many times does it look like? How many times does it look like it will take to rotate completely? Looks like 5. Yeah, I'd say 5. Yep. Okay, so that means we'll do 360, kind of like what Elizabeth said. We'll do 360 divided by 5 now. Okay, which is 72. Okay, 72 degrees. And then, of course, we have rotational symmetry in nature as well. So this lovely little flower. And how many times would it take to rotate this to get it back to its original? And again, we have to be a little bit lenient here with Mother Nature. She's not perfect. But again, we go like 1, 2, 3, and then 4 back to the original. So 4 rotations. So and what degree would that be then? 90 degrees. Whoops. I gotta put the division symbol there. So yep, 90 degree rotational symmetry. Okay. Now, we don't want to keep these things too separate, right? So I know I taught them to you separately, but if we go back here, for example, let's see here. Does the Batman symbol, does it have rotational symmetry? Yeah, no, not really. What about the picture here, the Taj Mahal? Yeah, it kind of does, right? If we were to rotate that 180 degrees, that'd be hard to convince us that that was not the original picture, right? I mean, in fact, it looks pretty original. On a quick glance there, it looks pretty much the same thing. And then, let's see, of course, what about the moth here? Does the moth have rotational symmetry? No. Yeah, no, I wouldn't say so. What about this orange? Yeah, it does, right? Okay, so I think, let's see here, it would take, oh my gosh. So if this is the top, it'd be 1, 2, 3, 4, 5, 6, 7, 8 turns. So it'd be 360 divided by 8 for that rotational symmetry. And of course, its point of rotation would be right in the center of that orange or grapefruit or whatever you want to call it there. And let's see, that would be 45 degrees. Is that right? Yeah, 45 degrees. Okay, how about the snowflake? Does it have rotational symmetry? Again, forgiving Mother Nature for not being perfect. Okay, does it have rotational symmetry? Yeah, right? So let's see, again, if I call this like the top here, it's going to go 1, 2, 3, 4, 5, and then back to the top 6, so 360 divided by 6. It's also got a 60 degree rotational symmetry there. Okay. And of course, some of these have line symmetry too. For example, what about this recycling symbol? Does it have line symmetry? Yeah, well, let's see here. If I were to draw a line down the middle, like this, I'd have a flat side here trying to reflect over to an arrow side here. So does this have line symmetry? Yeah, not really, not exactly. I don't think this guy quite has line symmetry either. The flower kind of does, though. If we, again, forgive Mother Nature, we can kind of like draw actually 4 line symmetries there, I should say. Okay. So the flower does kind of have some, if we kind of do it like that, and like that, and like that, right? Got some line symmetry there. Okay? Alright, so as a little task for you guys to try here before we get too much further, what I would like you to do is on a spare piece of paper or a scrap piece of paper, or maybe if you can squeeze it in here if you want to, that's up to you, wherever you'd like to, I want you to kind of draw a little design. I'll just do it on this, I'll just draw it here so you can see it. Okay, I want you to make like a little Venn diagram. Well, this is unlike, you guys know what Venn diagrams are, right? Anyone not know what a Venn diagram is? It's okay if not. Alright, so I figured you guys will talk about those now. I don't know, though. Who knows what things have changed since I've been out of school? Okay, so we're going to look at the symmetry of the alphabet. Okay, specifically we'll look at capital letters. I think it's T-A-L. I believe so. Okay, so the capital letters. So here's what we're going to do. We're going to draw one circle. Okay, and that circle will be for a horizontal symmetry. Horizontal line of symmetry. Alright, and then we're going to do another big circle over here. And this is going to be vertical line of symmetry. And then one more down here, and this will be rotational symmetry. Now, you might be like, but Mr. Whitmire, there are these overlapping sections. What do they mean? So, you have this like space right here in the center. So this space right here in the center is reserved for what kind of capital letters? They should have horizontal, vertical, and rotational symmetry. Right? So horizontal, vertical, and rotational symmetry letters go in this section. Right? What kind of letters go in this section right here? What kind of letters go in this section right here? If they have what? Rotational and horizontal, right? And then the letters here are both rotational and vertical. The letters here need to be horizontal and vertical, but not rotational. And then only horizontal, only vertical, and only rotational are in there. Okay? So go ahead. A through Z. Again, capital letters, A through Z, capital letters. And of course, if they don't have any of those, where should we draw those? Outside. Outside, exactly right. Yeah, not within any of these pictures here. Okay? So go ahead and give it a shot. I'm going to do it too because I haven't done it yet. Okay. Yep. So, for example, take a look at letter A. Capital letter A. What kind of symmetry does it have? Does it have a horizontal line of symmetry? Like, could you draw a horizontal line through that? So it would have vertical. Now, could you rotate it and make it map onto itself? Make it like match up with itself.
Like turn it.
Mm-hmm.
Yeah.
So you could, but how would you have to turn it? You have to turn it 360 degrees, right?
Yeah.
There's no, so 360 degrees, we don't count that as rotational symmetry because everything would have symmetry. Would have rotational symmetry, would have 360 degrees. So the only thing this is has a horizontal line of symmetry. So you'd only put it in this section. Sorry, it only has a vertical line of symmetry, so you'd put it only in this section. If it had both a horizontal and a vertical line, you'd put it in this section, because that's where those two overlap. If it had both a vertical and a rotational, you put it there. If it had a horizontal and a rotational, you put it there. And if it had all three there. If it had none of them, you leave it on the outside. You write it on the outside.
Also
So.
got it.
And I understand some of us may disagree about letters because we write our letters differently, but question? Oh, you're just thinking.
Just like
Mm-hmm. We didn't leave a space for that, so I would just leave it out. mirrors. All right, anyone still need more time with the letter activity exercise thing? Nope. All good? All right, so let's see what we came up with here. So how about horizontal line of symmetry? What we got? Evan.
B,
Okay.
D,
D, okay.
C,
Uh-huh.
E,
Uh-huh.
K.
Yeah, that's what I got too. B, D, E, C, K. B, D, E, C, K. Okay. That only had horizontal line of symmetry. Okay. How about anyone get anything for horizontal and vertical? Alone, but not rotational. How about volunteers for vertical? So yeah, Hunter.
Oh, I got something in the middle. Y. Like
Oh, you
the
did?
Y is not going to be one that much.
Right, okay. Yep, that's okay. But so then what'd you get for vertical then? So
AMYTW.
AMYTVW. I think of one more.
Oh, U.
You, yeah, exactly. Yep, you. All right, yep, good. How about, did anyone get anything for rotational and vertical line of symmetry? Yeah, no, me neither. Okay, how about, and then rotational symmetry. Rotational symmetry, so Patrick, what you got?
Well, depending on the angle you make it at, Y could be vertical and rotational.
Depending on how would you, like, what do you mean by how you draw it?
If all three of the lines are 120 degrees to
Oh,
each other.
I see what you're saying. Yes, if you make your Y, which, okay, that, so you're saying like, almost like that kind of Y? Okay, fair enough, yeah. That could have rotational as well as a horizontal line. Okay, that's true. So we can put like a Y with a question mark there, depending. Okay, I like that. Okay, and then how about rotational symmetry alone? Rotational symmetry alone. What we got here? Drew. N. Is that it?
That's all that I got.
Okay.
Z and S.
I also said Z and S there. Again, it depends on how you write your Z's and your S's, but I would say I could see Z and S being the same thing. That's right. Okay. How about anyone get rotational and a horizontal together? Rotational and horizontal together?
That's where I put my
Okay.
Yeah, that's where I put my Z.
Oh, you put your Z there. Okay, let me think here. So, a Z, if you were to take your Z, yeah, and flip it down, it wouldn't quite match up, would it? So, yeah, no, it's blank. All right, and then for the very center, Evan, what you got?
All right. H, I, X,
Uh-huh.
and O.
And O, yeah. And that's kind of what I got. So there's left. And so then the guys, the poor leftovers there are F, G, J, L, P, Q, and R. Okay. So yeah, something like that. Okay. So there they are. Okay. Now, pass out these mirrors because these kind of assist us in determining line symmetry, okay, to kind of convince us. So for example here, just a quick like kind of use of it, I know we can, I mean some of the stuff is like, it's like so obvious, Mr. Mario, why do we need to have this toy in front of us when we can just look at it? Well, I guess I hear you, but sometimes it's fun to have this along here just to see. So the way the mirror works, okay, first of all, there is a upside and there is a top and a bottom to this mirror, okay? So the top side, okay, is kind of like the normal edge, and the bottom edge is this kind of like beveled edge, okay? It's kind of like more narrow towards the bottom, so that's going to be the bottom edge. And you want to have the beveled edge kind of facing you and on the bottom, okay? And so what you can do, for example, is if you take this like Batman symbol and turn it sideways, and if you put your mirror right over the line of symmetry, or very close to where you drew your line of symmetry, it like, you can you can make it like match up. You can actually reflect it. If you look into the mirror and you adjust it, you can make it so that you can see exactly how close. You can reflect the one side of the bat symbol onto the other side of the bat symbol. You guys see it there? If you want to look, you look into your mirror there to see it. Okay, you can kind of like match up. And again, you have yours upside down there. I know it doesn't matter too much, but there you go, there you go. It doesn't matter too much, but it's nice to have the edge there. So you can see that, right? Okay? Same thing with like the moth here. If you take your moth, you can kind of like manipulate things around to make it, you know, see just how close those two wings really do match up. And sure enough, it matches pretty closely to that line of symmetry there. Okay? Works for the orange as well, right? If we take the orange and just pick one of those lines of symmetry, you can kind of like line up the two parts of the orange so that it like matches up perfectly. Okay? If you want to be like really precise, that would be the line of symmetry that you actually draw, not the one that we kind of like sketched in, but that would be like a really good line of symmetry because it's like literally reflecting. Okay, you can even reflect the Taj Mahal there if you wanted to see how good its reflection was in the water. It's pretty close. Okay, there's some like not quite right there, but it's pretty close. Okay, you can see that. And then of course there's like the fun little thing too is that it makes red things on the board disappear. That's kind of neat too. Spell this out. It's gone. It doesn't really do it to the stuff on the board. It kind of like, I don't know what it does. It like highlights it a little bit when you look at the projector, but it makes it disappear on the board. So, there you go. Now you know how Cyclops feels, right? When he was in school, his teacher couldn't use the red marker because he'd be blind. Okay. Actually, I used to have a student in one of my calculus classes, and she was colorblind to red. So whenever I would write red on the board, it would look like you guys are looking at right now through your paper. I don't know what my red marker. Oh yeah, my red pen on my paper disappears too.
Yep.
So you can see it's like it makes my paper's writing disappear. And you guys all look so silly with those things in front of your faces too. It's also one of my favorite things too. There you go. Anyway, I look like Cyclops.